I'm Kil, and I'm an illustrator, and I'm an engineer at Klarna, and I work on a programming language called Krishna, which is oriented towards security, and it's also oriented towards non-programmers, so it has to have a time-traveling debugger so people can actually see what their program is doing and go back and forth. And I have the chance to actually work on a similar debugger at Klarna for production, and that's what I want to talk about today, that kind of experience. Um, Now, this talk is going to be divided in 3 sections. In the first section, we're going to go through a small interactive debugging session of a little toy program. And then we are going to see what kind of technology makes this kind of debuggers possible, and what kind of trade-offs you should expect when you do this in production. And then we're going to close with some of my personal thoughts. So let's get this started. And for this to work, you have to use your imagination a little bit. So imagine that you're a marine biologist, which means that you study the ocean. So you dive, you collect data from the ocean, you turn that data into numbers, and you try to make sense of those numbers. Today, those numbers do not make sense, just like in computers. So you're kind of tired, kind of sleepy, your bed looks kind of inviting right now, so you decide to take a nap. You soon fall asleep, and you have a very strange dream. So in the dream, you're floating deep underwater, and you don't have a scuba equipment, but it's not like your lungs are crushing or anything. But hear someone say something from behind you, and turn around to see this very regal woman, and she's like, "Pardon, doctor, could you help me fix the ocean?" You don't understand. We turn around to where she's pointing to anyway, and she's like, "Is the reefs to see? Are you seeing the reefs? It's not like there's anything obviously wrong with the reefs. But it's odd, because the ones you're familiar with usually have more fishes, more colors. This one does not have that. But you have no idea why it doesn't have that. Now, if only you could observe more of it, maybe you would come to a better conclusion, or you could form more better hypotheses. The problem here is that observing the ocean takes months or years, and you don't have that kind of time. But she's like, "But there is a vampire squid who logs everything around here." Logging? You know that. If you could at least take a look at the logs, maybe something would stand out to you, and then you would know where to look at. So you swim toward deep waters looking for a squid. You find her, and you're like, "Hey, have you got any logs on the fish's health?" She's like, "Yeah, sure, but do you really want that?" And you're not really sure why she's kind of confused, hesitant, but you kind of understand when she starts throwing everything on top of you, because there's just too much data. There's too much stuff happening at the same time, because there's just too much stuff in the ocean. And it's not like you can actually follow this in any reasonable manner or understand any of this. So you feel kind of overwhelmed. And she's like, "Yeah, there's a phantom jellyfish, and she does trends, she does correlations, that kind of stuff. And yes, summaries look nice. At least with the summary, you could have a broader view of the whole system, and then maybe something would stand out to you, and you would know where to look at. And this correlation stuff is not really that unknown to you. You've heard of it before. It's only, well, it doesn't matter. You search for the jellyfish anyway, and find her. She's kind of big. And you're like, "Have you got any trends on the fish's health?" And she's like, "Yeah, sure." It shows you this graph, which kind of shows that the health in the fish population has been in steady decline over the past years. Not good. So you find something that looks bad. You're excited. But you kind of wonder, is this one of those kind of things where some of the fishes are doing really, really badly, and the other fishes are doing kind of all right, but the averages are kind of flying to you? So you ask her for the deviations as well, and she plots that in, and there isn't much of a difference. Oh no, you're back to square one now. You know that something is bad, something wrong is happening. You have no idea why. You have no idea where to look at. Now, if you only had more science to go on, maybe you could look at other stuff, and you would find better things to form a hypothesis on. Of course, you have no idea where to look, and that's the problem. So I tell her that, and she's like, or it could look for the sea bunny. You have no idea what to expect. But at this point, you're kind of taking any leads. So you go, find the sea bunny, and tell her your story. And she's like, oh yeah, you can actually just observe the ocean, look into the past. You don't understand. And she shows you this miniature aquarium. She's like, if you turn the dials here in this aquarium, you can look into the past. You do that. And you see that these fishes are swimming towards the corals, which is kind of their food, but they're not eating. They're just swimming away. Oh, that's odd. They're supposed to eat. But it's not like this is telling you why they are not eating. You found a problem, you have no idea why that problem happens. So tell her that, and then maybe I need to look at other stuff. So for example, from your work, you know that changes in the environment actually affect the fish's behavior as well. So if you could observe that, maybe you could form better conclusions. And she's like, oh yeah, you can actually just do some code and make that happen. And do that. And write some code, and it puts this big red overlay on top of the aquarium, and it gets redder as the ocean gets warmer. So the ocean here is getting quite warm, which is bad. Now, the other thing that you know from your work is that when the ocean gets quite warm, the corals begin to die. And that's bad because that's kind of the food. And you plot that in as well with some more code, and you see that these corals are actually not doing very well. So you've come to a hypothesis that looks sensible to you, that would explain actually all of the problems that you've seen so far, and that's the ocean gets warmer, the corals begin to die, the fish stop eating. Problem solved. Clearly, that's just a hypothesis. You have no idea if that hypothesis is actually true. So if you actually try to fix the problem based on this hypothesis, and it turns out to be wrong, you'd only know months afterwards, years afterwards. And at that point in time, you have much worse problems. So ideally, you would likely want to be more correct, or more likely to be correct, before you start solving the problem, even if you have a hypothesis that looks sensible to you. And I tell the sea bunny just that, and she's like, oh yeah, you can look at the future as well. You don't understand. It shows you this old aquarium. She's like, we have a hypothesis. You can make some assumptions that would make that hypothesis either be valid or not, and then you can look into the future of this system. So I make two hypotheses. One is that the ocean warmth is constant, so it doesn't change, and the corals are all healthy. So under those assumptions, we expect the fishes to actually eat, and that would solve our problem. So simulate the future of this aquarium under those assumptions. And what you see is that the fishes swim towards the corals, they eat, and then they swim away. And then they don't die, which is what they expect to do. Which means now you have a validated hypothesis. And you can actually try to do this in production and see and have a more likely, higher likelihood of succeeding in making this plan in that interaction. And that's how we save the ocean. That's the end of this talk, right? Well, I'm not debugging the ocean. I guess most of you here are also not debugging the ocean. So what happens when you hit these exact same problems in a different system? How do you go about debugging it? And how do you go about debugging it? Through the same kind of debugging flow. And when I say the same kind of debugging flow, it's where you have a hypothesis of what's wrong, and then you make some observations of your system, and that may turn out that your hypothesis was not that great, so you refine your hypothesis. You might keep doing this a lot of times until you get something that looks sensible and feels sensible. And then you come up with a plan to actually fix the problem, and you put that plan in action, and then hopefully things go all right. And to do that, in this little simulation, we've used this kind of cute debugger, but it's actually two debuggers. One allows us to look into the past, and it's called a record and replay debugger. So you can look at exactly what happened in the past at any point in time. And the other allows you to look into the future and see what the system would do under some assumptions that you have in the present. Now, these two debuggers actually use the same technology underneath. It's kind of similar to film. So if you record what your program is doing over a period of time, then you can replay that program as many times as you want. Just like you can replay a movie as many times as you want, you always get the same movie back. And you can play it backwards or forwards, it doesn't matter. It's recorded. So the technology that we are looking at is this, and it's not a new technology. It's been around for quite a while. But for us at Klarna, there are some weird constraints that meant that we can't just take any record and replay debugger, put it in production, then problem solved. No, because our recordings actually can spend several years. You can't really record years of whatever your server is doing. That's not going to fit anywhere. We also had to have this always enabled in production because you can't really predict when a problem is going to occur in production. You'd have to be able to debug it. And of course, because of these two things, we need these recordings to have a very low overhead on our actual production system. So that was kind of unique. As you can imagine, the naive implementation of just recording everything does not really work because there's just so much memory that you can fit in a single computer. Now we can, of course, compress these states, so you only keep the initial state and then only the changes after that, and then you can save a lot of space that way. But you run into a separate problem, which is the resource contention, because your computer is not really just running your recording program or only your server program. It's actually running a lot of stuff that's containing for very limited resources. And if you run more stuff, everything's going to keep running, but it's going to keep running much slower. We do not want that, because it turns out that our server is actually serving real users and not actually want to impact these users. We want to keep them very happy and very smooth, the experience of them using the system very smooth. And if you start doing a lot of expensive stuff in production, that's not going to happen. Now, the thing is that a lot of things that you run always on in production actually do sampling. So for example, if you run profiling always on in production, it's probably using sampling. So you sample some data at some point in time, and some more data at other point in time, but you have no idea what happened between those states. So for example, if you have the Visual Studio Debugger, you actually have the same sampling approach where you put breaking points in your code, and you can switch back and forth between those breaking points because it records the actual program state at those points in time. But you have no idea what happened between those. And if anything non-deterministic has happened there, you have no way of actually debugging that in any sensible manner, which is kind of a problem in production because we need to be able to debug this big void. Because in production, you don't really anticipate these problems. If you could do that, you would just fix the problem. And we need to be able to debug this without restarting the server and going to the customer and say, hey, can you perform this action you took into the system like 3 months ago because I need to debug it? That makes no sense. So I need something more accurate. And the more accurate alternative is tracing. So imagine that you have a program, and you record everything that your program does, so every instruction that you run. And you have the history of execution or the trace of the execution. Now, if you imagine your program as a graph, this means that you record every node in the graph that you hit in the order that you hit them. Of course, that's still too much, because if you look at how many instructions a Beam program has, it's just, you cannot record that in any sensible manner for years. So the thing is that you don't really need to record everything. Because if you have the source code, and if you have a pure instruction like x0 = 1, you can always replay that from the source code without any additional information, deterministically. So every time you replay that, you get the same state back. So you don't need to record that, which is great. That gets rid of a lot of data. But you do need to record all of the non-deterministic stuff, of course. Because, for example, if you have a random number generation, every time you run the random number generation, it returns a new number. So you need to be able to replay it deterministically afterwards. So you have to record any additional information that would make that function deterministic. In case of the random number generation, that could be just the return of the function. But if you affect the file system in some way, you need to record also information about this external system that you've affected. So that increases things a little bit, but we still have this very cheap trace, just the instructions, that you can actually know everything that happened in the system at any point in time. Except, if you look at this, we actually only have the trace. And if you want to know what was happening here, you actually have to run this interpret in your head and then figure out how the state has changed over time. That doesn't really work. We are just human. So the thing is that you can reconstruct these states if you have this trace. And for that, you need this stepping function. So the stepping function is just some function that takes the previous state of your application, or according to your trace. It takes the next instruction to run, or the next recorded non-deterministic instruction to run, any additional information that it needs to actually make that instruction deterministic again. So you can replay it the same way over and over. And then it computes the next state of your application. Great. For our case, we actually need this to all of the states to be in memory at the same time, because we actually replay the program backwards as well. So we need to be able to go backwards in time as much as we want and have immediate feedback. So we can't afford to replay everything from the start over and over. Now, if you use persistent data structures before, you know that with persistent data structures, you can actually have all of these states in memory at the same time. And you don't pay for all the states, but you only pay for all of the changes to the states that you make. And the Beam now has the maps, which are really great for this, because you pay a very constant amount of memory every time you make a change. You don't pay for a whole new map. Now, if you're familiar with compilers, interpreters, that kind of stuff, you notice that this is kind of very similar to writing a DSL. Well, it is. Your trace is actually a linear instruction set. And you put them through this weird machinery, and out comes all of the states that your application has run into in this period of time. Now, once you have your stepping function, once you have its trace, and once you have some initial states, this actual weird machinery is just map-fold out. You don't have to do anything else. And if you want all of the states in memory at the same time, list map-fold out gives you exactly that. If you don't need all of the states in memory at the same time, and you need to be more conservative about your memory, you can use a streaming map-fold out. And then you don't need to change anything else about your program and get constant memory. But you have to replay the program from the start if you need to go back in time. So with this weird machinery, you can actually look at all of the state of the program, like all of the database records at each point in time, all of the connection between those database records, and you don't have to replay this in your head. It's just there. It's just, you just look at it. Now, of course, the results contention is still there, because the recording, we made it cheaper, but it's not free. And if you're recording at the beam level, that's a lot of information. So we need to make these traces less granular if you want them to span over years of data. And the way you make less granular, you just you decide what you really want to observe in your traces. So if you trace at the machine level, which some debuggers do, you can observe things that were happening in the machine. So things like memory stores, things like cache timing, even things like how your branch predictor did misbehave in some kind of structure. You can observe all of that that was happening in the machine at that point in time because we recorded it. If you trace at the beam level, you can observe everything that happens in the beam during that point in time, even if you replay this trace in a completely different machine. Now, if you play it, record your domain level stuff, you can only observe things about your domain, directly at least. Of course, as you go towards your domain, you get much cheaper traces, so you can record more stuff or a longer spans of time. But you can observe less stuff as well. As you go towards the left, towards the machine level, you can observe much more stuff about the machine that was running your code. But you can record much shorter spans of time because there's just too much happening. starting at your domain level usually makes sense, because usually you reason about your program or what your program is doing in terms of your domain. And only if you notice some very specific portion of that code that could have something to do with your encoding or the machine that was executing that, then you can run some more detailed analysis on that specific portion. So you don't have to rerun this over 8 years of data. So this is basically what you do. It starts at the domain, and if we find something that needs more investigation, then we find the smallest portion of the trace that needs more investigation, and then we do more analysis at a lower level. Now, the other thing to notice here is that the only thing that you want to do in production is recording the traces. We don't want to replay the traces in production because that's too expensive. So for replaying, we have a separate production node where we send the traces to, and then we can do any analysis that we want, as if we were rerunning that program in production, in the production machine, because the result is always the same, regardless of which machine we replay it on. So it allows us to do very expensive analysis on a separate node without affecting our actual users of the service as much as we want, as if we are doing this in production. And this is also the approach that local time travel debuggers take. So if you take things like RR or Pernosco, who trace at the lower level, they are actually recording what the machine is doing at a certain period of time. They record that to a binary file. And when you exit your program, you load that binary file in a separate debugger, where you can then replay that program over and over again, as if it was in the original point in time at the original machine, as much as you want. And you can even send that binary file over the network to some other machine, and then you can ask other people to replay that program for you as if they were running in your machine. Now, this is great and all. You can actually recover all of these states, but you need some way of visualizing them, because you are not going to look at the actual internal database records and in any sensible amount of time over several years. That also does not work, because it's just too much information. So the thing is that your traces and your states are just data. So if you can write any program to transform your data in any way you want, or analyze your data in any way you want. So for us, we want to keep most of this stuff in Erlang. So the replay part is kind of 1,000 lines of Erlang code and generates all of these states that we keep in memory. And then we compress these states, because once you serialize them, you don't have that guarantee from persistent data structure anymore. So you have a custom serialization that basically gives the same memory guarantees on the JavaScript side and serialize them, send it as JSON to the browser, and then we visualize them as an interactive debugger, where you can click on any event over the past years and see the exact state of the database at that point in time. And the actual JavaScript code that we wrote is just a few hundred lines of code of JavaScript, very straightforward. Just take some JSON, put it on the screen as some HTML elements. And if you have a reactive library, or if you use some, for example, LiveVion, you can actually keep this more in the Erlang side if you want. So you have a visualization, great. But how do you know that it's the right visualization? How do you know that this is answering the questions that you need to answer? Well, for us, we just looked into the past kind of incidents that we had, saw all of the problems that we got, and all of the questions that we could have asked that would help solve that problem faster, and kind of put that into boxes or modes of debugging, and build different visualizations specialized for each kind of these questions. So if you want to learn something X about your program, you look at visualization X. If you want to ask a question Y about your program, you look at visualization Y. And they kind of show different relationships between these objects, which you might be interested in. And so you don't have to do those relationships in your head as well, and some computations as well. Now, it might be very tempting to just keep adding stuff to it, because why not? You have the data. But that's a bad idea, because For example, for this debugger, which we've built here, it was very useful for answering the question, why are the fishes not eating? But if the question was, the fishes are swimming in a weird behavior, why are you doing that? This would not help, because it does not highlight that kind of weird behavior of the swimming. It's just a lot of information going on the screen at the same time, and you have no idea where to look at. So if you want to scan this very fast and go over several years of data, that doesn't help you, because you have a lot of attention to irrelevant details that should not be there. So just keep your visualizations more like streamlined towards some common questions. Of course, you're going to get the non-common questions as well, because there's production and things happen. So what happens when you get the things that your visualization does not help you to actually answer? And well, one answer to this is what Amy did in her PhD thesis. So she worked on this thing called the Y-line debugger. The Y-line debugger is a record replay debugger, like the ones we've solved here. And you record your program, you replay your program, you stop your program, and you notice that there's something that looks odd. And let's say your program is a drawing program, and there's a circle there that should not be there. And you click on the circle, and there's a bunch of questions that you can ask. And you ask, why is the circle red? It should not be red. Why is the circle red? And the Y-line debugger actually do some program analysis over the source of the program and surface all of the information that's relevant during that execution that would cause the circle to be red. And for example, it might be that 10 minutes ago, you had a variable that said a equals 1, but actually a should equal 2 at that point in time. And then 10 minutes later, that meant that you took a few branches that turned the circle into a red circle instead of a blue circle, which is not great. So the thing is that you can do this very expensive analysis, very intricate analysis, once you have these traces. But that's not what I'm really suggesting here, because if you're going to do this kind of program analysis in your specialized time-traveling debugger for your domain, you're going to spend a lot of time, a lot of resources. That's just not very efficient. But what I'm suggesting is more like the general idea behind her work, which she described it as using debuggers as an augmentation, and I call as seeing debugging as a conversation with the computer. So basically, instead of the Y-line debugger just showing you what's wrong with the program, it helps you ask questions, and then the computer answers those questions in some way, and then you refine your questions, and you keep looking at the refined hypothesis of what's wrong until you find the actual problem. Now, you may be familiar with that because the REPL is just that. In the REPL, you have some questions that you want to ask. You type some code, you get an answer, and then you refine your questions. You type more code, you get another answer, and you keep doing until you're satisfied with what you've learned from that system. So if you have a time-traveling debugger that's on the browser, it's very easy to actually just put a text box where people can actually write some arbitrary JavaScript code, and then they can analyze the actual states that are just JSON data as much as they want for the context that they are facing right now. So you don't have to actually predict those things before they happen. And if they happen very often, you can just put them back into the debugger. It's not that difficult. And the other thing that I want to talk about is speculation, because we've seen that as well. You can actually look into the future of the system. How do you do that? I already have it. You have a stepping function. That's 90% of the work done. So the only thing that you need to do is that you have to be able to simulate your effects, even when you don't have the additional information that allows you to replay it deterministically. So once you do that, you can actually simulate the program for as much time as you want. And it helps if your system is actually modeled as a formal system. So if you have your system as an interpreter to begin with, you can just call the original interpreter. And if you have your system as like a state machine, you can just call the original state machine. And then you record that, of course. And this also allows you to change the past. So if you, for example, in the while-line debugger, we just replay up to a certain point and keep asking questions. But we can also replay up to a certain point and say, yeah, I don't want to replay this part of the trace anymore. I want to replay this other part of the trace, which was what I expected to happen, and has some other assumptions about the execution of the program. And then you can see what that program would do under that different timeline. So if different things happen at that point in time. And you can compare these timelines as much as you want, because you can go back and forth as much as you want and get the same timelines back. Of course, as long as you can undo your effects. So if you affect an external system, that might be difficult because you have to actually simulate that external system as well. You have to record stuff about your external system. That usually does not go so well. And for us, most of these effects were kind of local, so it wasn't really a problem. But if you have something that does a lot of HTTP calls to external service, you end up just mocking a lot of stuff. So what have you learned about this? What I have learned is that observing things is really hard. So we have all of these kind of debuggers that you can use to observe things in your system, but none of them actually replace each other. So for example, you would argue that observability replaces logging, but who has not used printf debugging when they were just trying stuff out? Printf debugging is really cheap, and it's really useful. So we keep using the same stuff, even if we have things that give us more information, because the trade-offs that they make is kind of different. So logging is very useful because it's very cheap, and it gives you enough information. But if you have a server, you can't really look at everything that's happening, because that's too much. And that's where observability comes, because that allows you to search for exactly what you want to look at, and you correlate stuff that only shows you what you really need to look at in order to understand what's going on. Of course, observability breaks down when you don't know what to search for, because then you can't do anything. And that's why record and replay really shines, because you can just record stuff, and then you can replay it and observe different aspects of your system as it evolves, and then you can learn more about where you could look at. Oops. Of course, this doesn't come for cheap, because record and replay debuggers, especially the specialized ones, you have to maintain it. You have to write it. And so you have to dedicate some resource to that. For us, it didn't really take that much resources, so it was about a week of a project to do all of the replay, all of the visualization. And it's like 1,000 lines of Erlang code. That's nothing. But if your system is not already modeled as a formal system, and if you don't have like this very specialized instructions that you do instrumentation on, then you might need to do more work, because you have to identify also what are the effects that would help you reconstruct the state of your application at each point in time. For us, it's already an interpreter, so you could just build it very cheaply. And if there's anything that you take out of this talk, I hope it will be that if you can't observe things in your system, you can't debug it. So if you can increase the amount of ways in which you can observe things, and you can reason about things or do analysis on these things, dynamic tracing, which is what I've shown here, is really cool. And you can not just do this kind of record and replay debuggers, but you can actually take it to the next stage and do actually dynamic analysis on it as well, or improve static analysis with that kind of trace, if you have it. Of course, that's more work for you. So yeah, that's what I had. And thanks for listening. And if you want the slides, it's on this URL below. And there's also links for all of the stuff I've talked here, including the papers and the other debuggers that I've mentioned that you can, or you can actually use in any system that you want without doing anything, because it records at the machine level. But if you use it for the beam, you'd record the beam running your program, and then understanding what that exactly means afterwards might be a bit of not so great. Yeah. It also does not really work well with concurrency. But yeah, so that's all I have, and we can go for questions now.
All right, we have a couple minutes for questions. All right, do you have questions in the room here?
Yeah, thank you, Q. Really great presentation, something bright in our boring engineering world. My question is about how you actually implement it in the code. So do you really put all these debugging lines of code into each function, or how does it work in your code?
So for us, the actual tracing is done by recording these instructions to a database, because we have this. So our system is designed as an interpreter, so the instructions are already there, so we don't have to do anything to do more tracing. If you need to do further instrumentation because the system is not designed as an interpreter or as a formal system, then you can either do like a specific, what is it called? Specific instrumentation, where you just like a log, you send that information somewhere, which you already do, for example, for observability. You send these events to some kind of system that's going to collect them. Or you can use redbug as well, or DBG. So you can trace specific functions in the beam without changing your code. So you can use trace specifications for that. The thing is that if you trace at the beam level, you have to be very careful, because you want your trace to give enough information for you to reconstruct the states. And you have to be very careful about what you trace. You also don't want to trace too much, because that would be overloading your system.
Cool, thank you.
All right, do you have more questions here in the room? All right, and also for people remotely, and for you if you want to ask questions later, there's the Huva app. So again, thank you, Q, for the talk.
Thank you.